Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Battery Tech webinar, Enhancing Lithium Ion Battery Performance through Advanced Slurry Analysis, sponsored by Hioki and Waters TA Instruments, and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few announcements before we begin. First of all, this webinar is designed to be interactive. On the right-hand side of your screen, you'll find the Navigation Center, which will allow you to learn about our speakers, download resources, and participate in the Q&A session that takes place at the end of our presentation. If you experience any technical difficulties, refresh your webinar console within your browser window. That's usually as easy as hitting the F5 key, or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance. And lastly, before you leave us today, please complete our webinar survey, as your feedback provides us with valuable information on how we can make future events better for you. And now on to the presentation. Discussing today's topic is Dr. Christopher Scholz, Director of Product Marketing at Hioki Corporation, and Emre Baburoglu, Ph.D., Field Application Scientist at Waters TA Instruments. And to learn more about our speakers, just visit the Info tab in your Navigation Center. And Emre, thanks for joining, and over to you.
Thank you, Michael. That was good pronunciation. So thank you everyone for coming to this talk where we'll be discussing how rheology and impedance can be used to characterize battery electrode slurries. So first, I want to give an overview of how these slurries are made. So we have three components: the active material. This is where we store the chemical energy. So this is, if it's a lithium-ion battery, this is where we store the lithium ions. Examples of these include things like nickel manganese cobalt oxide, so NMC, and lithium iron phosphate, so LFP. And then we also have a conductive additive. This is because the active material particles themselves are usually not that conductive, and these allow electron transport to the active material particles. And examples of these are things like carbon black, carbon nanotubes, usually some sort of derivative of carbon. And then we also have our binder. This provides mechanical stability to the final electrode, and this is usually some sort of polymer. And we mix all of these up in a solvent, making a slurry, and then we coat it at a specific shear rate and thickness, and then we dry it, in which case it stops being a slurry, because the slurry is a word for the fluid form. And then we calendar it, and then we have a final electrode that's ready to go into the battery. And we in rheology are really quite good at characterizing the formulation, mixing, and coating processes, because these slurries are what we call non-Newtonian fluids. So their microstructures depend on the mechanical stimulus that we apply. And I'll explain how rheology can be used to characterize these processes. But first, what I want to do is to draw sort of a microstructural picture of what these slurries sort of look like. So what I'd like to say is the relationship between active material particles and carbon black is a bit like the relationship between a spider and its web. And I'll explain what I mean by that. So if we look at the left, if we look at the size of these particles, a carbon black particle is very, very small. So it's in the order of 10 nanometers. So these particles can sort of float in solution. And once they find each other in the solvent, they stick together via van der Waals forces. And if enough of them stick together, they form a sample spanning gel that's actually quite stable. Whereas the active material particles are much larger, so 1 to 10 microns. So the attractive forces that might keep them together are not strong enough to keep them together compared to their weight. So they just sediment. And so, like the spider needs the web to hold it up, the active material particle needs the conductive network, or the carbon network, to hold itself up. And the binder here is also involved in increasing the viscosity of the solution, but since it's dissolved, it doesn't impact the rheology nearly as much as the other two particles. And going back to the spider analogy, the spider relies on vibrations from the web to catch its prey, and the active material particle relies on electrons from the carbon network to reduce the incoming ions, or lithium ions if it's a lithium ion battery, but it could be zinc ion, sodium ion, depending on the battery technology. And if we lose web connectivity in the spider web, then the spider will fall and maybe die. I'm not actually sure if it died, but we're going to say it dies here. And likewise, if the carbon network loses connectivity, the active material particle will sediment, and this will cause the slurry to phase separate and will cause inhomogeneity in the slurry, basically. And so the takeaway idea from this slide is a dispersed carbon network is not only important for the conductivity of the slurry, but also its homogeneity. Okay, so now we can talk about some processing parameters. So one of the most important processing parameters to optimize in slurry processing is the formulation. So how much conductive additive do I actually need? If I have too little conductive additive, then we might not have a continuous carbon network. So electrons might not get to every active material particle, and so they basically become wasted and they're not utilized, and they might sediment, and so we might get some dead spiders. And then if we can also have too much carbon black. This time we do have a continuous conductive network. It's even more stable actually, but this time we're not maximizing the energy storage capabilities of our electrode. So the name of the game is basically to maximize the amount of energy stored per volume. So, maximize the amount of active material particles while minimizing the amount of carbon black in the formulation, while also having a sufficient carbon black to have a continuous conductive network and deliver electrons to every active material particle. So there is a happy medium here. And there's quite a lot of ways to characterize how much conductive material is in your slurry using rheology. I've given one example here. This is called a flow sweep, where we measure viscosity as a function of shear rate. And as you can see, as the concentration of conductive material, so in this case it's carbon nanotubes, that's what CNT is, increases, the low shear viscosity also increases. And then we also see that as this conductive material increases, we have increased shear thinning. So the rate of the decrease in viscosity as a function of shear rate increases. And other very important processing parameters to optimize are the mixing and coating processes. I've sort of lumped them in together here because they're sort of rheologically similar processes. So if a slurry is undermixed or coated at a low coating rate, these carbon black particles can agglomerate. Again, we lack a continuous conductive network, and we don't get to the active material particle, and some particles sediment. Yet that's why I put a dead spider there. They can also be overmixed, so this can cause the carbon black particles to adhere to the active material particles, which means that they're not part of the continuous conductive network. Again, we don't have effectively enough carbon in the network, and again, that's why I put a dead spider there. And lastly, we can also have aged slurries. So if you just leave your slurry out for too long, these carbon black particles will aggregate, because their most stable thermodynamic state is when they maximize the contacts between each other. So if you think of a web, this is a lot less contact between each other than an aggregate is. So they naturally aggregate, and then the two phases separate, and you get inhomogeneity, non-uniform distribution across electrodes, and a dead spider. And perhaps the most common way to characterize the coating and mixing processes using rheology is called the Spectroscopy test. This is sort of what it looks like. We first apply a very small amount of shear to characterize the structure at rest, and then we apply a higher shear that is representative of the coating or the mixing process, which causes the slurry to decrease in viscosity, because these slurries are shear thinning. And then we reduce the shear rate again to sort of the rest state and watch the slurry recover to its original or close to viscosity. And we can tell a few things from this test. So the first one might be drying time. So you ideally want to know the slurry viscosity at the time of drying. You ideally want your slurry to be completely recovered before it's dry. You can compare initial versus final viscosity. If your initial viscosity is much larger than your final viscosity, this might mean that your coating process is not fully dispersing your slurry. If your final viscosity is much larger than your initial viscosity, then your mixing process before the coating process is not fully dispersing your slurry. So coating is actually dispersing your slurry more in this case. And lastly, you can also inspect the thixotropic recovery speed. So this is basically how fast this viscosity recovers, the slope of this curve in the third stage of this graph. And if this happens too fast, we might get leveling issues. The film might take on the characteristics of the blade that it's coated with, which might not be very uniform, so it won't naturally level out. And it might also be too slow. So in this case, we might just get a runny film that's non-uniform. Okay, so we talked a bunch about how rheology is really good at characterizing these slurries, but one deficiency of rheology, it's very much a bulk measurement. And if we look at the composition of these slurries, they are really mostly made of the active material particle. So in this case, in the slurry, it's 90% active material particle, 5% binder, and 5% carbon black. And the signal that we get from rheology is a non-trivial combination of all three of these components. So if you want to isolate the carbon network, then we have to do an electrical measurement. And that's where impedance comes in. And this idea, I think, is explained really well in this study right here, where two slurries are compared, one mixed using a vortex mixer and one mixed using a planetary mixer. So for context, a planetary mixer is much preferred in industry because it's able to go to much higher shear rates. And if we look at the rheology of these two slurries, so this is a flow sweep, they look, quite similar. So you can say that maybe they differ a little bit in the lower shear range, but one might say that's within error. Whereas if we look at the impedance spectra of these two slurries, the vortex mixer has a much higher impedance than the planetary mixed slurry, which is implying that we have a much better, more dispersed network when mixed using a planetary slurry, which makes sense. And so TA Instruments' solution to this problem is called the Rheo-Impedance Spectroscopy Accessory, or Rheo-IS. And this is sort of what it looks like. It situates on top of our advanced Peltier plate, which is one of our simplest temperature control options. So we have two electrons along the bottom here, electrodes, excuse me, that's separated by an insulator. So that's how you do the electrical measurement. And then we do the mechanical measurement using this spinning top plate. And the cool thing about this design is that we're basically able to utilize the full torque range of the rheometer. And if we compare this to some designs that you might have seen in industry, like they all have some sort of limitation. So this wire design, where we have just wire contacts to the top and bottom plates, you're able to get a very good impedance measurement, but you're only able to do oscillatory tests. So you can't do full rotation because the wire gets tangled up. In the spring contact design, you are able to do a full rotation, but your torque range is very limited, and you have a much weaker impedance signal because it's basically just a loose wire that's contacting the top plate as it's spinning. So you don't get a very uniform solid contact. In this electrolyte design, so this time instead of a wire, we have an electrolyte bath that's completing the electrical circuit. And this time we're able to do, utilize the full torque range of the rheometer, but now we're limited by the electrochemical potential stability window of this said electrolyte. And yeah, so this is sort of a zoomed out view of the rheometer using the Rheo-IS, so it's connected to the Hioki LCR meter. We can control temperature from 0 to 100 degrees, and we can measure things like impedance, resistance, conductivity, reactance, and permittivity. Okay, so now I'll go through some simple examples of how rheology and impedance can be used to analyze these slurries. And perhaps the simplest way that impedance can be used to analyze these slurries is to just pick frequency to measure impedance, and then look at how it changes as a function of time or temperature, or during shear or after shear. So this is what has been done in this study. Reactance here is just impedance, so you might know it as imaginary impedance. It's the same thing, but you can also pick real impedance or resistance if you want. So here we're applying a shear rate of 500 reciprocal seconds, and viscosity and reactance doesn't change during shear. But then as we reduce the shear to 0.01 reciprocal seconds, we see that the slurry recovers both in reactance and in viscosity. But they have very different time constants. So the viscosity recovers much faster, than the impedance does, which is telling us that even though you might think that the slurry is completely recovered, the carbon network might not be, further highlighting the need to do impedance as well as rheology. In this study, two slurries are compared with different conductive material loadings, 2% and 4%, and impedance spectra taken of these slurries at very low shear at the start, and then very high shear, so 1,000 reciprocal seconds, and then after recovery. So that's what's meant by the quiescent state here. And in the 2% carbon nanotube slurry, we see that impedance increases quite a lot during the high shear, and that's because we're basically breaking up all of the carbon-carbon bonds, so the electrical signal doesn't have as clear of a path to travel between electrodes. But then once we remove that shear, the slurry recovers, and impedance decreases to what it was before. Whereas for the 4% carbon nanotube slurry, we again have this increase in impedance when we apply the high shear, but when we remove it, impedance is actually lower than what we started with, which is implying that we now have a better, more dispersed slurry, which sort of implies that it wasn't very dispersed to start with. So there is some problem with the mixing process of the slurry, or it might also be overloaded with excess carbon nanotubes. And lastly, I also have another study where we compare two different slurries. Again, we see if we look at the rheology of these two slurries, they look fairly similar, but then we do impedance as a function of shear, and in slurry 1 it looks like we get the same exact impedance spectrum as a function of shear, so at every shear rate, whereas in slurry 2 impedance increases as a function of shear rate. So this is implying that the slurry is getting more and more dispersed as we increase the shear rate, again implying that it wasn't very dispersed to start with. So preliminarily, sorry, slurry 2 is the worst slurry, and then these slurries are made into electrodes by coating and drying, and then they're examined using scanning electron microscopy. So they're just looked under a fancy microscope, and you can see electrode 1 looks a lot more homogeneous than electrode 2. Electrode 2 looks a lot more clumped. So visually also electrode 2 looks worse. And then these electrodes are put into a cell for testing, and you can see electrode 1 retains a much higher discharge capacity at higher rates than electrode 2. So this study is basically showing that we're able to tell how good the slurry is using impedance and rheology without going all the way to making a battery and testing, which takes many hours. And now I will pass the torch to Chris to talk to you about how impedance can be used to analyze these batteries.
Excellent, Emre. Thank you very much. Yeah, so I'd like to drill down a bit more into the impedance from the electrical engineering perspective applied to electrode slurry. The question is, how can we, is there a way of predicting the quality of the slurry without going through the whole process of making electrode sheets and making batteries? There's a lot of experimentation going on. There's a lot of gut feel. There's a lot of trial and error. That is expensive. And we want to reduce that. We want to figure out, so you have a set of slurry measurements, impedance measurement of different slurries, like I'm showing on the right-hand side of the slides. And you really want to know, is there a difference in dispersion state? What's the degree of network formation? Are there variations? Can you detect lot-to-lot variations? So we want to have a deep insight into the morphology of the slurry by just measuring impedance. Impedance is a relatively easy measurement. We also want to have a method that is applicable for research and development, of course, but we also want to scale that into pilot lines and possibly volume production. So quantitative, we need a quantitative measurement. We want to be able to detect faults. And ultimately, when you from the research side talk to your production facility or to your vendors, you want to have a common language that gives the same measurement between different organizations and different groups within your organization. So here's what I'm proposing to do. All right, you measure the impedance in Nyquist plot or cold plot, whatever you want to call it. And then there's a very powerful tool that we electrical engineers call equivalent circuit analysis. Right, so you take the measured data, fit them to a equivalent circuit topology, and get a bit more into the details on what that looks like, and then extract numerical indicators, so quantitative indicators that give you a measure of the quality and the topology of the slurry. So that's the overarching idea. And you can do this for different temperature, for different mixing stage, for different shear conditions, all the things that Emre was showing you earlier. So let me step back a little bit and talk very briefly about equivalent circuits and impedance measurements. So when you do an impedance measurement, concept is very simple, right? You have your slurry that's the Z or Z if you're outside the US. That's this box here. And you apply a voltage, a varying voltage, a voltage with a certain frequency. You scan the frequency through a certain range, and you measure the resulting current that that results from basic wiggling all the material that's in your box, and you see the response. So the response will have the same shape, but it will be delayed, and it will have a different amplitude. Right, so in mathematical equations is I0 times sine x plus a phase delay phi. Then you take the difference or the quotient, the ratio of voltage and current, and call this complex valued impedance. That's the impedance Z. You can write this either as a phasor, right, with a phase delay and an amplitude, or you can write it as real and imaginary part. And a very common way of plotting in electrochemistry is to plot the real part on the horizontal axis and the imaginary part call this reactance on the vertical axis, and you get the Cole plot or the Nyquist plot, depending how you want to call it. Instruments that do that, I've got a picture of a Hioki impedance analyzer, various other instruments out there that do that. So it's a pretty standard methodology. You wiggle on the material inside that you want, you measure the resonances, electrochemists call it relaxation properties, and plot the results. So everything electric that we have in the slurry, we know by wiggling at it. This is a behavioral measurement. Right? We don't look at the physics inside. We measure what comes in and what comes out. So it's a behavioral model. Now there's a method in electric engineering called equivalent circuit model, where you identify the behavior and matches into known circuit models. The main models are resistance R, that really restricts the flow of electrons. You have inductance, that's a storage device that stores energy and passes on later. Capacitance, and a very unique element, the CPE, the constant phase element, that's unique for electrochemist. There's a pseudocapacitor that accounts for non-idealness of chemical materials, roughness, porosity, all this kind of stuff. So equivalent circuit modeling is a powerful way of understanding what the electric measurements, what the impedance measurements that you're doing, what they actually mean in heuristic terms. Okay, so with that, let's look at what we do with that. So we have our equivalence, we have our impedance plot, the Nyquist plot that we measure with the impedance analyzer. Then we do the analysis, we analyze the equivalent circuit model. And the third step is to identify 3 numerical indicators that give you information about the slurry, the topology of the slurry, the quality of the slurry. So you can quantify it and you can measure it. We call them DCR, so it's related to the resistance. We call it the second indicator Rratio, and the third indicator, we call it uniformity. And in the remaining few minutes, I go through the details of what these indicators actually mean. So let's start with the DCR. DCR is the DC resistance. It indicates the resistance of the flow of the electrons through the slurry. So that's a way of quantifying the conductive, additive, and the solid content of your slurry. Ideal state is, and that's not quite correct, but it's not completely wrong, ideal state is to have a low DCR. The way how we measure, so there are different ways of measuring the DC value of a slurry. Right? You can look at the Cole plot and extend the tail that goes to 0 frequency that intersects with the real axis and this orange point. You could extend the half circle of your relaxation measurement and define the intersection point with the real axis as DCR. Now we are using the equivalent circuit model that's somewhere in between. The advantage of the equivalent circuit model is that the data or the measurements are more reproducible, more stable. Again, it's a heuristic model. It's used for comparison of different slurries. So we have the DCR value. Let's get to the next indicator. That's the Rratio. So the Rratio is the contribution of the different materials, active material, conductive, additive, binder, to the total resistance. We're mostly interested in the conductive material. So when I talk about Rratio, I'm talking about conductive additive, the ratio of conductive additive relative to the total resistance. This is an indicator of how much conductive material you have actually in your conductive path, and that's what you want. Right? That's a very important indicator. It gives you information of the morphology of the material and the length of your chain. So ideal state is an optimal value, not the lowest, not the highest, but an optimal value. So let's drill down into this a little bit more. So here are a few Nyquist plots for different materials. You see the various relaxation constant. It can be relatively difficult to figure out what material is actually in there, right? If you look very careful on the top left curve, you see basically two relaxation constants. When we use our equivalent circuit model and curve fit the model to the measurements, those are the golden dots. You see some very good correlation. That's typically how the materials work. And you see in the top left corner, you see three different dots, two orange dots, one blue dot. And the orange dots are the peak value for the different materials in your slurry. So for example, on top left corner, we have the CNT and we have the NMP, and then we have the DC value, which is the blue dot. Similar for the other materials. Let me move on. Yeah, so we have an excellent fit to the measured data, and we can clearly identify the contribution to each of the relaxation processes for the different parts, different constituents of the slurry. So with that, we can identify the resistance for each contribution to the slurry, for each component of the slurry. So that's the diameter of the semicircle. So for example, here the RNMC has a certain diameter, the carbon nanotube have a certain resistance, and then we add up the resistance value from the equivalent circuit model, right? That's the diameter of the circle, and get the DCR, which is our DC resistance. Taking the DC resistance, or taking the, let's say the conductive additivity of carbon nanotubes, the resistance of carbon nanotubes divided by the total resistance, we get the R ratio. So the R ratio, mentioned this earlier, right, is the contribution of your conductive additives to the total resistance. Okay, let's move to the third indicator, that's uniformity. Fairly intuitive what uniformity is. Uniformity gives the distribution and size of the conductive materials. Right? It impacts bad uniformity, low uniformity gives you defects, and it gives you variation in your electrode sheet. Obviously, you want to avoid that. The ideal state is a uniformity of 1. How do we measure uniformity? Again, based on the equivalent circuit model. Right, so we have our resistance for the different constituents of the material. We have our CPE. We're taking the CPE value and comparing it to the ideal circle. Right, usually the capacitor in the complex plane gives you a circle. Right, the circle is usually not ideal, so you have an exponent p that is less than 1, and that shows how broad, how non-ideal the actual measurement is relative to the ideal circle. So P of 1 is an ideal circle. P will always be less than 1, and that is the indicator of the uniformity. So that's kind of the broadening of your relaxation. Okay, so we have the 3 indicators, DCR, R ratio, and uniformity. So what does it all mean? So I like to look at it in two ways, or in 2 different plots. I like to look at the R ratio and DCR in an XY plot. So plotting the R ratio on the horizontal axis from low to high, and DCR on the vertical axis from low to high. And then we're looking, so I mentioned ideally we want to have low DCR, so we want to be in the lower left corner. But we also want to have a high contribution to the conductive path from your conductive additive. Right, so this means when you have a low resistance but a high a low R ratio, this means that the particles are not well mixed, the conductive particles are not very well mixed, they're agglomerated. The ideal point is when you have a low resistance and a high R ratio, right? So have long path that forms and give you good conductivity and low resistance. When you start mixing more or when you add more additives, you start having dispersion, and at some point you chop the conductive path into a smaller chains. That means that your resistance goes up, your R ratio might go down. So the sweet spot is on the lower right-hand corner, a good R ratio, optimal R ratio, and a low resistance. For uniformity, same thing, right? You want to have a uniform distribution of your particles, and you want to have a uniform size. So by looking at these three parameters, R ratio, DCR, and uniformity, you can get some clues on the morphology of your slurry and adjust your processing parameters. So let me give you a few examples. We have slurries with different, so in this example, we're varying the size of the carbon nanotubes. Right, so with carbon nanotubes from 1 nanometers up to 10 nanometers, and we measure DCR, R ratio, and uniformity for each of the slurries. If I look at DCR, right, the lowest resistance is at 1 nanometer. That would be the ideal slurry if you only look at the resistance. Then I look at the R ratio. Right, I do have a broad peak. Between 1 and 6 nanometers. The optimal point there is at 4 nanometers. And the uniformity, right, 1 is good, 4 is reasonable well, and then it starts dropping off until you reach the maximum of the particle size. So looking at all that, it becomes very clear that the particle size or the carbon nanotube size of 4 nanometer is ideal. Right? You have the peak in the R ratio, you have a low DCR, and you have a good uniformity. So that's just one example of showing how to optimize a slurry. So the next question, of course, is, does it really work? Right? So far, those are just measurements that. What about the electrode sheet that we built out of these slurries? Well, here are the results. We're measuring this with our electrode sheet measurement tool, where we can measure the composite layer and the interface layer, the resistance of the composite layer and interface layer with one setup. And looking at the results, sure enough, right, at 4 nanometer particle size, carbon nanotube size, we have an optimal point. So that is a lot of material in a short time. I want to pass the word back to Emre to wrap up this presentation.
Thanks, Chris. Yeah, so just to wrap up, we have some take-home messages. So if there's anything that you remember from this presentation, these are 3 main things. So the carbon network provides conductivity and homogeneity to the final electrode, so not just conductivity. Rheology measures the bulk, while impedance isolates the carbon network, and we can compare the morphology of different slurries using electrical impedance, using these parameters called DCR, R ratio, and uniformity. So yeah, that's all we have, and I think we can take questions.
Terrific. And thank you, gentlemen, for that presentation. That was terrific. And before we get to our Q&A, let me remind you to participate. Just click on that Q&A icon in your navigation center, then type your question into the available text box before clicking send. And if we're unable to answer all submitted questions, we'll be sure to share them with our speakers who can reply to you offline. So let's get started with a question from Charles, who asks, what is the difference between coating versus mixing from a rheological perspective?
Yeah, great question. So they're actually quite similar in that how we would characterize them would be unidirectional shear and thixotropy. They would have slightly different shear rates. Mixing usually would be in the order of sort of hundreds of per second, whereas coating would be usually thousands, and mixing just takes longer. You would mix it for much longer than you'd coat it. So effectively, coating time would just be determined by the thickness of the blade that you use, because that's the only time that that the slurry experiences the shear effectively.
Keep the questions coming. This one from Lloyd, who asks, how would you use the rheometer to optimize the mixing process and ensure you're not mixing too much?
Yeah, another good question. So there's a few ways to do this. So what I would probably do is just mix the slurry for a set amount of time, probably a small amount of time, and then take the slurry to the rheometer, measure some signifier, whether that's impedance, yield stress, or its modulus, and then go and mix it again, take it back to the rheometer. If those signifiers increases, so the yield stress increases, modulus increases, or the impedance decreases, that probably means that you still have to mix your slurry. And if those decrease, you're probably over mixing. If it stays the same, you're probably done with mixing.
Yeah. And if I may ask, right, so you can also look at the R ratio, right? When you see the R ratio first, when you start mixing of agglomeration, so you have a low R ratio, you keep mixing, you get an optimum point, and then it decreases again. So you have a maximum point for the R ratio, and that's kind of your sweet spot where the mixing is at the best point. So monitoring that during mixing, you can get a lot of information on what's going on in your slurry.
Okay, thank you for that. Keep them coming. This one comes from Ivan, who says, most slurries are solvent-based. Will there be any issues with solvent loss using Rheo-Impedance?
It's a good question. No, we actually have a solvent trap cover that prevents evaporation. So yeah, it would, especially with these slurries, yeah, it should do a pretty good job over the course of a couple hours.
Okay, great. Good to know. This one from Shimon, who says, can you explain why there's a third wire, a green wire, for the impedance accessory?
Yeah, I'll just go back to the impedance accessory. So the third wire is called the guard, and it just it basically guards the measurement from stray inductances and currents. So if the current that we apply through between these two electrodes charges something else, then this sort of makes it go to null, so that we only measure the material.
Okay, that being all the questions we have today, I'd like to thank you. We appreciate your time and expertise on today's topic. Also, thanks to our sponsors, Hioki and Waters TA Instruments, as well as to everyone in the audience. We appreciate your attention and participation. And within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your peers and colleagues who might not have been able to join us live today. On behalf of our guests, Chris and Emre, I am Michael Krieger. Thanks for your time and have a great day.